Good morning. My name is Cengiz Alasinoğlu. I'm from Packet Design. Steve and I did a detailed analysis of ISIS in Qwest backbone, and I'm going to talk about this. Shankar from Qwest originally was going to co-present, but unfortunately he couldn't make it. Okay, why do you care about subsecond convergence? Well, the number one reason, if there is a failure and if you can converge in subsecond times, you actually have a higher availability in your network. The second reason is there are new services that the providers would like to support these days, like voice over IP, ATM, or TDM emulation over IP and such. Second, if we have subsecond convergence, we can actually get rid of all those level 2 really expensive protection screens like Sonet. Unfortunately, we are nowhere close to that number. Typical times are in tens of seconds, and definitely we need to do better. And we can do two things. We can either get rid of all the IP routing and put something else in place, or we can figure out what's wrong with IP and fix it. So our approach was, let's do some measurement, find out what's wrong, and let's separate myth from reality. And if there are things that we can improve, perhaps figure out what's wrong and fix it. For that, actually, we have been collecting ISIS traces from several ISPs. At some time, I asked Danny McPherson, how many ISPs he thinks are running ISIS. He said, from the top 15, he thinks that about 12 is running ISIS. I don't know how he defined top 15. But he said, from the top 50, it's about 16 or 17 or something like that. So a lot of the top 50 actually run OSPF, but the real big ones are actually running ISIS. Given the numbers he has given, I could say actually I have analyzed 30 to 40% of those ISPs who run ISIS. So even though the data I'm going to show is only from Qwest, actually most of the conclusions apply to all of those networks. In the Qwest backbone, we collected multiple, actually four week-long ISIS packet traces. We were actually very surprised. The first 3 weeks of the collection, we had absolutely no routing change on the path that we were monitoring. It was extremely stable. It was very good. And then that was, of course, not that good for analysis because we wanted to figure out when things fail, how long it takes to converge, and what we can do about it. Finally, in the project, we had a couple of routing changes that we carefully measured. By analyzing the data, we looked at how is the ISIS churn and whether it is stable, unstable, whether they will go to an unstable regime. And we also looked at during convergence what happens, how long it takes to detect and propagate LSPs and such. Anyway, from these we come up with a recipe which would get you subsecond convergence in a backbone just like Qwest. This is our setup. So we have the Qwest backbone in the middle. And we have two hosts connected to Burbank and Houston. These hosts, typically, they just establish a passive ISIS peering with the routers. And basically, any ISIS packet that the network sees, we see also in those two locations. And in addition, we have a constant stream of UDP packets going from our one host to the other. It is up to about 1 megabit per second. But on the average, we send a packet every 6 milliseconds. So this allows us to actually detect a link failure very precisely, within 6 millisecond error. And it's much faster than actually what the routers can detect it. So it actually tells us when the failures happen. And using the ISIS packets and such, we can actually tell how the convergence is progressing. Well, our typical path looks just like in this picture. So we are in the Burbank, and we have two hubs in Burbank POP, and then we jump to the Los Angeles POP, and then there we go to the Houston POP, and then another two hubs we are in our other end. The other dotted links will be used during the convergence. But I don't think I need to go into details of the ISIS, but just to refresh, when a link fails, you have to do the following in order to have ISIS converge. First, you need to detect there is a link going down or up, or there is a peer reachability problem or such. And the most preferred way of doing this is hardware detection. It is the fastest. But if it was to ever fail, there is a software mechanism called Hello Protocol, And it is slower, but it does provide detection. Second, once you detect that there is a change in the network, you have to generate a link state packet, which records basically that a link has gone down or it came up or what. And then this packet is flooded through the network. Flooding usually happens in link propagation delays. It's actually extremely fast. However, at each hop that is processed, it has to be received, it has to be processed, and then further forwarded. So it doesn't really take the, if you can think about it, take it to the slow path of the forwarding as opposed to the fast path of the forwarding. At each place, at each router, it has to go to the routing control plane and before it can go to the next one. So there is some processing delay associated with it, but it should be comparable to edge-to-edge link propagation delays. However, there are also limits which slow down the propagation. Once every router receives this new LSP, now they have a new view of the network and they run basically a Dijkstra's shortest path first algorithm to compute the new routing tables. This computation is resource intensive, especially for full mesh networks. And hence, yesterday, for example, Chris told us from Cable and Wireless, he told us that a couple of years ago they had a network meltdown. That was because of this computation. And it's a full mesh level 2 network, and hence it took so much time, and if there is a lot of churn in the network, your routers can go into mode there. Only all they are doing is SPF computation. I'll talk about it in a little bit. So because of that, SPF is also rate limited. When a link state packet comes, you wait multiple seconds before you actually do this routing computation. So to study this effect, we looked at the ISS churn and instability. So what do I mean by churn? So each time there is an event happens in the network, a link goes down and up, a new LSP comes. So I define the churn to be the rate of this LSP, that is, number of LSPs that our host received over a period of time. This is important because usually each change requires an SPF computation, unless you have the rate limit. Well, and it's also expensive because each time there is something changing in the network, you have to run the SPF algorithm, and that takes CPU resources. But if your CPU is too busy, if you have high churn, and your CPU is too busy doing the SPFs all the time, the second detection mechanism, the hello protocol, is very time sensitive. And if you are busy and you start missing your hello packets, you start missing sending your hello packets, then the other end of the connection may think that you're down. If you miss 3 of them in a row, then you're out. And that actually, what would that make is that it would falsely bring down that adjacency. Okay, we had churn, we had busy CPU, and then we brought more adjacencies down, hence we have more churn in the network. That becomes like a loop. And you can't get out of it once you put it in. I mean, once you have churn and then you go to busy CPU and then start missing your hellos, then you start missing even more hellos and then so on till your network maps. And that did happen to Cable and Wireless a couple of years ago, as Chris told us yesterday. So the rate limits for slowing down SPF, so doing it once every 5 seconds or so, is actually introduced because of that. So did we see something like this in the Qwest network? Well, the first thing we look is if there is such a thing happening, there should be hello packet misses. Is there any hello packet misses? Or is it ever like, instead of sending once every 3 seconds, is it ever like once every 6 seconds? And this is how the hello behavior looked from our 2 hosts, even though this is only showing one of them, the other one is more or less identical. On the x-axis is the week that we picked this data from, and the y-axis is the milliseconds inter-hello time, and it's supposed to send us 1 every 3,000 milliseconds or once every 3 seconds, and it is doing very good. There is this thick band to it, but that's by the protocol design. You are supposed to introduce some jitter. You don't send it exactly 3 seconds. You want to send it a little bit earlier and later so that there are no synchronization effects. And at both ends, routers were working really well. They were sending their hello packets just like a clock. But with this, we can only analyze the instability at that router. There may be another place where there might be a problem, and for that, we looked at the ISS churn. Again, on the x-axis is the days of the week, and then the y-axis on the graph on the left is the number of link state packets we received per minute. So you can see most of the week is actually very steady, constant, about 30 link set packets per minute, or once every 2 seconds there is a link set packets coming. Except for the beginning of the week where there is this high churn region, where it is like about maybe twice as much. And then there are occasional spikes. Well, this is actually, majority of the churn on the graph on the left-hand side is because of the LSP refreshes. ISAS actually requires you to send, even if there are no changes, requires you to send a link set packet every 12 minutes or so. And the churn that you see on the left is actually majority of it, about 98% of it is that refreshes. If you subtract from this the refreshes, what you get is the physical churn, which is the graph on the right-hand side. That is, these are actually, each point here actually has a new topology change recorded in it. And that one is actually less. It's actually less than 1 a minute. So we find the network to be extremely stable actually, because the SPF times takes about in this network 30 milliseconds, and that's about true for majority of the networks who don't have full mesh level 2 full mesh layer 2 network underneath. And one change a minute, and you have to do 30 millisecond worth of computation is nothing. Next, we wanted to look at how this churn distributes across different routers. So on the graph on the left, the x-axis is the percentage of routers. You can see majority of the routers, almost 100% of the routers, sends about 800 LSPs. And this is all refreshes. That is, majority of the routers have nothing to report during the week. The network is extremely stable. Except there are like 8 of them. They send a lot more. So any churn that I have shown this prior is because of these 8 routers. So churn it is really localized. The graph on the right-hand side is the same for links, with the y-axis replaced with the number of flaps a link changes state. Again, all the way almost up to 100%, the links don't change. I mean, they are actually always up. And again, about 10 of them, they have really high churn. So the network in general is very stable, but there are problem routers and problem links that needs to be looked at and see what's happening. Next, I'm going to show a problem router, the worst router here, and then followed by the worst link and how they actually flap. This graph shows over the course of the week number of link set packets generated by that router, that one single router. The y-axis is the link set packet sequence number. So during this short period at the beginning of the week where I circled, this router generated about 3,000 link set packets, whereas the rest of the week it generated roughly about 600. So during this initial very short period of time, it had actually 110 times more churn than the rest of the week. And these routers, actually 2 routers, this is one of the 2, are responsible for the extra churn that I showed at the beginning of the run. So something fishy is happening here. Why would it generate that many? And this is an unstable link, the link that was flapping the most. The y-axis is up and down. As you can see, it's up and down and so forth. And in the protocol, there is no protection against a link like this. And this thing, even though the x-axis is only over an hour in this graph, actually goes on for more than a day. So this link could not decide whether it's up or down that day. And there is no protection against a link like this in the protocol. Think of this as a wavefront coming at you. And if you, for example, without doing anything to stabilize this, if you, for example, play with the interval timers, like how often you do SPF and such, you may actually go into trouble. Again, here though, the link goes down in about 30 seconds and comes back up in 8 seconds. So that's, again, not that a big deal, because each time you have to do an SPF on 30 milliseconds, you can actually deal with this wavefront. But if you have many links which are like this, or if they are all simultaneously, if there are 10 of them are like this, then actually the rate is a lot higher. If you have full mesh, a physical link change like this will probably cause you hundreds of virtual layer 3 links having this behavior. And then you have a huge wavefront coming at you and you need to be dealing with it. So how do we deal with such an unstable link? Well, currently what we have is rate limiting. What we do is we don't do the SPF right away once we receive it. When we receive a link state packet, we wait for 5 seconds in case there are other events happening in the network. We capture all of them we bundle them all of them into a single SPF computation. But what does this mean? Okay, now we can save the network from melting because we restrict ourselves to do no more than one SPF computation every 5 seconds. But we are ignoring change in the network. Some of these changes are actually legitimate. So instead of converging, we are actually ignoring the change. Hence, it will have really bad effect on convergence. Is it possible to actually converge fast at the same time deal with such big wavefronts, such big instabilities? Yes, it is, and it's nothing new here actually, even though it is not part of ISAS. There is a good recipe because you want to be converging really fast when a link fails because there is data flowing on it. So you want to be adapting very fast to link failures. But it's not so for when a link comes back up. There is no data using the link that was down. So it's okay if you take your time to slow it down. That's what we call asymmetric up-down filters. Basically, you want to be detecting bad news fast. You want to be rerouting the data that is using that link. But when the link comes back up, you can slow down. And this is the key thing to making a filter which will take a wavefront like that and actually get something which is manageable. The second component of this is adaptiveness of it. The more the link is unstable, the more you want to be slowing down that link coming back up. Of course, we can always have an incremental SPF algorithm which would also reduce the CPU utilization on the router. How would that work? The graph on the left that I showed you before is the wavefront coming at you. The graph on the right-hand side is basically applying such a filter with an exponential backing up and then with a 20-minute maximum to it. What happens is basically links goes down. The first time we penalize it a little. It comes back up again. If it stays up, no problem. If it goes down again, that time we penalize it twice as long. If it was 10 seconds, we now penalize it 20 seconds. If it comes back up and stays up, no problem. But if it goes down again, we penalize it further. And so forth. Eventually, it becomes 20 minutes. That's our maximum that we put into the filter. So after that, for the rest of the time, for the rest of the week, actually it takes about maybe 40 minutes or so to get to that 20-minute point. And then from then to the rest of the day, where this link is unstable, we only check this link once every 20 minutes. So you have a wavefront that is on the left that you cannot deal with, and you can actually filter it down to something that is manageable. And there is nothing really new here. This treat the bad news fast and the good news slow has been around a long time. It's not part of ISAS. And the way we damp is no different than BGP route lab damping. It's just an analogous way of doing it at the link state. So nothing really magical, but unfortunately it's not in place. I suppose I'm emphasizing that fact because this is a simple recipe. To sum up, 3 of the 4-week long data collection periods, we have no route change on our path. And the churn is only caused by few links, and we think that this network is extremely stable. On the 4th week, we have some link failures, and we had measured the convergence. And I have to say, it's the fastest you can ever have with today's technology. It's really good. However, there is still a lot of room for improvement. So where does the convergence delay come from? Basically, a link fails. That's where you start your timer. And then every router in the network has new routing tables. That's when you stop. That's the convergence delay. And what do we do during this time? First, we have to detect the link has gone down. Second, we have to generate a link state packet and flood it across the network. And then once we receive it, we start this SPF interval, the typically 5 seconds. So that introduces a 5-second delay. And then eventually we do the SPF computation itself. So we are going to look at all these 4 steps in the Qwest network. And why do we care about fast convergence? Well, by design, and this is not a bug, and this is not this is by design. During the convergence, you can have routing loops, you can have black hole routes, you can have suboptimal routes, and this is by design. And it is designed so because it was assumed that the convergence is fast. So if it takes if the convergence is subsecond, say 100 milliseconds or so or whatever, then it's not a big deal if we have such outages. Because designing a system which doesn't have any of these is very hard. So we don't have to solve that problem. But unfortunately, in reality, convergence times are long. Hence, these are a problem for services like voice over IP or TDM over IP or whatever. Here is a link failure. The red link on the network between I have to use this hand, between the router in Los Angeles and router in Burbank fails, and we need to reroute around it. In the graph, the green line is the excess delay of the UDP system that we are sending. That's basically delay minus the propagation delay, minus the constant component of it, or what Steve calls it, absolute jitter. So as you can see, we are receiving, we are sending and receiving packets very regularly, and at around here, I don't know if you can make out the hand. Anyway, at around here, the link fails, and then there is about 8.5 seconds of nothing. We don't receive anything, and then link comes. I mean, the routing reconverges, and we have a new route, and it's longer. It takes more delay. And then it proceeds again. And during this time, we have about 1,300 packets lost. That's a 1 megabit per second stream, and out of that, 1,300 of those packets are lost. So the convergence takes basically 8.5 seconds. And why so long? We need to figure out what goes into this 8.5 seconds. The first component is detection, and that's actually very easy for us to measure. So this is the same graph. To that, I have actually put the 2 dots, one here and one way here. This one is the reception of the link state packet coming from the Burbank host. So the host the router. The router at the Burbank detects the link has failed and generates a link state packet, and our host receives it, and we put it on this graph at this point. And it takes about 3 seconds. So this is very fast for it to be hello protocol. This is actually layer 2 or below detection. Maybe it is hardware, maybe it is some other layer 2 protocol detecting the link failure. 3 seconds is still not acceptable, but it is not hello protocol. The router at the Los Angeles actually is receives this, generates its link state packet around here, which is 20 seconds, which is really late to detect it. This one is definitely hello protocol, because by default in a point-to-point link, you send a hello packet once every 10 seconds, and you need to miss 3. That gives you a window of detection from 20 seconds to 30 seconds, depends on when was the last hello sent around here. So you can have up to 20 to 30 seconds detection delay. So definitely the router at Los Angeles had to rely on hello protocol to figure out the link was done. So hardware detection on that side did not work, but it seems to have worked in the Burbank, but it's still slow. But nice thing about link failure, it's sufficient that one router detects it. You don't need to wait for the other one. You know the link is done as long as one router tells you it is done. So in this case, the magic number for us for convergence is 3 seconds. So 3 seconds of that 8.5 seconds goes to detection. There is still 5.5 seconds that we need to count for. The second component is, once we generated the link state packet, we need to flood it across the network. So we need to propagate that LSP. And this is what I call LSP propagation delay. And we measured this actually. How do we do that? This is our host in Burbank, and then this is our host in Houston. You look at the link state packets generated by this router, the router R1. When he generates a link state packet, he floods it. So we immediately receive it at Burbank. The link state packet floods across the network, goes over all sorts of paths, and eventually we receive it at Houston. So when we receive it at Burbank, we timestamp it. When we receive it in Houston, we timestamp it. We take the difference. That's approximately the link state propagation delay. And this graph shows that in this network, actually, when before the link failure, the link state packets approximately took 300 milliseconds to go across. When the link failed, the link was down for about a day, it's about 400 milliseconds. This is subsecond, so this is actually acceptable for our goal of reaching subsecond convergence. However, this can also be improved because you can actually see we have 6 hubs here, so there is a 50 millisecond delay per hub, and we have 8 hubs here, it's 400. So there is a scheduling constant, which is 50 milliseconds. Routers are not doing something, they wait for 50 milliseconds before they actually propagate your LSPs. That I have not talked to the vendors yet on this, what might be happening, but this is another component where we have room for improvement. But for all purposes, this kind of behavior is acceptable for subsecond convergence. You don't need to improve this, but there is room to make it even better. So we had 5.5 seconds that we need to count for. 300 milliseconds of it we have counted for, so there is still some more delay that we need to count for. And the third component is actually really big. It's the spaced intervals, and by default it's 5 seconds. So when the link failure has been detected, LSP has been injected and propagated, and you have received it, but now you start a timer which is about 5 seconds long. And this is the 5 seconds of that 5.5 seconds. This is the biggest component of convergence where the time goes. It's more than the detection, it's more than the propagation, it's more than anything in the network. So if you want fast convergence, there has to be a way to get rid of this timer. With this timer in place, or with this timer with such a high value in place, you cannot have fast convergence. So what can we do about it? Well, we need to figure out why that timer was in the network, because there's a good reason for it. I mean, yesterday Chris told us. And without fixing the problem in some other way, you cannot get rid of it. If you, for example, today you can set this timer to 0, well, if you do that, you will be probably in trouble. You shouldn't be doing that. However, if you can replace it with some other mechanism which provides you the same safety, then you can perhaps reduce it or perhaps get rid of it, depending on your comfort level. And what are its goals? It has 2 goals. One is to contain the CPU load so that you don't melt. And the second goal is, if when there is a link failure, you actually receive 2 to 4 link state packets, because both sides have to detect that's 2 link LSPs, and in addition to IS adjacencies, there's also IP adjacencies, and sometimes they can be in different link state packets, and that can be up to 4 link state packets. So it kind of like it captures all 4 into one SDF. Well, this timer actually, in our case, fails to do both of them. First, when it comes to capturing, for example, we have seen the detection at Burbank and Los Angeles was 17 seconds apart. 5 seconds is not enough to capture the 2 of them. Second, yes, it does contain the CPU loss, but it does that by ignoring change. And we have identified another way to damp that wavefront, that instability in the network, by using that asymmetric adaptive filters, and that will do exactly the same. As a matter of fact, it will do even better. Instead of 1 SDF computation every 5 seconds, after 3 of them, you will be doing 1 SDF computation after 20 minutes. So there's something to replace it, which is much better than this current rate limit. But actually, this rate limit hurts. It actually does things really bad for the network, and that's going to be the next few slides. Here is another reason to get rid of it. This is a link repair. Actually, a link repair, and this graph is actually the packets on the opposite stream from Houston to Burbank. When this link, when a link between router R4 in Burbank and Los Angeles comes up. So the other link was done, and we were using the path through Sunnyvale, and eventually we will reconverge into using again Los Angeles, but go to another router at Burbank. So again, in red we have the packet loss, and in green we have the delay. As you can see, when the link comes back up, there is a 1.5 second that we don't receive any packets, and we lose actually 227 packets in our stream. A link repairs, and we have packet loss. So there is nothing in the network which is physically failing. So how come we have a packet flows? So if they are not but on transit on a link, which will go away. It's a repair, it's a good news. Why would we have a packet flow? Well, during transient, actually you can have a routing loop. That's part of the design. And if you look at the delay, actually, it looks like there is a packet loop, because once the convergence has finished, the packets that come out of that stream first have high delay, and as they are unwinding, the packets have loops less and less, and the delay goes down, eventually stabilizes on the new path. So there is this 1.5 second of a long enough loop. It's actually a two-hop loop. Two routers are ping-ponging between two of them, but TTRs exceed, in our 1 megabit stream, exceed, and the duration is long enough for us to lose actually about 200 packets. So the convergence at least took 1.5 seconds. But this is a theory. There is a way to validate if there was a loop or not, and that's actually looking at the TTL of the packets that come. Because when we send the packets, they have a TTL of 64. When we receive it, they have 59. And if during this time, when the loop is unwind, we should see all of the ranges from all the way from 0 going up to 59. So that's in the next graph. Instead of showing the TTL, actually I am doing, even though I still call it TTL, I am actually subtracting it from 65. So I'm actually showing the number of hops the packet has took. So originally we have an 8-hop path. What we couldn't see in the previous graph, actually even before the routing loop, there is a region where we have a suboptimal route of 11 hops. And then we have the routing loop. And then here, as you can see in red, this is the TTL. The packets come out with TTL of 60, 58, 56, 54, and so forth, all the way down to 8. That's a loop unwinding. So the packets who went to the loop first, they loop the most. So their TTL is about to expire. So that's the highest. That is 64 for us. I mean, that's 60 for us. And because there's 4 hops, which is not part of the loop. And then the next packet has looped 1 time less, so it is 58. And the third packet looped 2 times less, so it's 56, and so on. So what is interesting is actually convergence did not start at where the loop started. It actually started earlier. It at least took 3 seconds or so. And during that time, we had a longer path and a routing loop, and then finally we had convergence. Why would you have the convergence take? Basically, for convergence, you have to generate this link state packet, propagate it across the network, and then start doing your SPS. So to have such a behavior, that means one router has done its SPS at this point, where the longer path starts. And it led to a suboptimal route. But instead of like doing it when you are synchronized, the second router actually took another 1.6 seconds. It actually waited even longer and did the SPS at this point and called the routing loop. And then finally the third router did the SPS and the convergence completed, because those 3 routers were the critical routers on our path, and then we now have the new one. So basically, even though the change probably occurred somewhere around here, by the way, because there is still detection delay for the repair. Anyway, the repair happened here, but instead of doing the SPS computations right away, there is something that is spreading out these SPS computations across at each hop about 1.5 seconds. What could that be? Actually, there is only one suspect in this network, because the only component which is that big or of the same order is the SPS interval, which is 5 seconds. Can this be the cause of this? Because propagation delays, we know, are in hundreds of milliseconds. SPS time itself is 30 milliseconds, so none of this can be the suspect. Only component is left, the suspect is the SPS interval. To know that, actually, we know that a router has done an SPS computation here. So 5 seconds before this, there must be a link state packet that triggers the timer. And a second router has done its SPF here. Again, if you go 5 seconds back in time, there must be another link state packet that triggers another timer. And the third router has done it here. Again, if you go 5 seconds back in time, you must get another link state packet that starts a timer. And those are actually very easy for us to find, because we know when the link state packets come. This is actually when the router at Los Angeles detects the new link is up. And if you go 5 seconds forward, you hit this point where the loop starts. So the router, whichever it is, this one, has started its timer upon reception of this link state packet. Whereas the Burbank detected the link up at this point, and if you go 5 seconds, this actually hits you exactly hit where the convergence happens. But why would a router, a third router in this case, do an SPF computation here? If you go back 5 seconds, you actually hit a totally unrelated link state packet. It has nothing to do with this link. But timer happened to have started upon receiving this link state packet. So he started this timer here, but then he did the SPF here. He also has the relevant information. He also knows that this link is now up. Whereas this router, he started his timer here. So how did he manage to do this SPF here? So he must have done an SPF actually in the middle of these two link state packets. He must have done an SPF after receiving this, but before receiving this one. So when this one comes, he was idle. So he saw the new link state packet. He says, oh, let me wait 5 seconds, and then he waits here. And then the Burbank the same way. So SPF interval actually spreads doing SPF across the network really badly and causing this routing loop to be that long, or the suboptimal route to be that long. It's actually hurting. The last component of the delay goes to doing the SPF itself. I asked Shankar at Qwest to go to a couple of the routers and give me the times for SPF, how long does it take. And he told me it actually takes about 30 milliseconds. 30 milliseconds with one subsecond convergence is nothing. You don't have to improve that actually. But it is possible to improve it, and here's how you do it. This is in red is the runtime of the Dijkstra's SPF algorithm. This is my implementation. It's still actually apples to apples comparison because I am still dealing with the link state packets. I have to hash the routers from those 7 bytes and to go to data structures and such. So it's comparable really to a router vendor's implementation. Mine is much faster. That's because first I have a much faster computer. I think typical routers are 200 megahertz CPUs, whereas my machine was a 1800 Pentium 4. So there is a factor of 10 there, and then another factor of 3. I'm probably a better programmer. Just kidding. Anyway, so it takes using, again, this is using the Qwest topology. It's not a random graph or anything. And using the real events of the network, that is the real link failures, all those ups and downs and everything. I mean, the flipping links and everything. It's this exact same event. One by one, I am doing a Dijkstra computation, and for the same event, I am doing an incremental algorithm. And this is how the incremental algorithm works. I mean, they look close, but this is in log scale. Actually, from here to here, it's 100 times better. On the average, actually, an incremental algorithm is 84 times better. What does this mean for you? If you don't want your network to melt down, if you just replace, do nothing else, but if you just replace Dijkstra by this algorithm, you can change that 5 seconds SPF interval to something 84 times faster, and it will not have any more CPU load than it had with Dijkstra. So from 5 seconds, you can go to 50 milliseconds, and it will have absolutely no more CPU load than anything else. That's good for that. But actually, if you look at the behavior of this algorithm, up to like 60% of the time, it's less than 10 microseconds. It's really, really fast. And up to like 98% or so of the time, it's less than 100 microseconds. In a few times, it's still faster, like 3 or 4 times faster, but you don't lose with this. However, with such a network like Qwest, with 30 milliseconds for SPF, you don't have to have this algorithm to have subsecond convergence. It's good to have, but it's not a must. What this algorithm is good for is actually scaling. This graph is by Habo Yu, a colleague of mine. On the x-axis is the size of the network, and on the y-axis is the SPF computation times. At the bottom is the incremental algorithm, and on the top is the Dijkstra. And this is again in log scale. This graph, actually what we need to look here is that the graph on the top is growing faster. It has a higher slope towards the end than the graph on the bottom. That means if you have an incremental algorithm, with using one level ISAs, you can go really large net sizes. You don't have to have 2 level ISAs, or you don't have to worry about how long it takes to do SPF computation. And this is basically a Dijkstra algorithm has an log n scaling, whereas the incremental algorithms, amortized complexity of them is actually log n. So that's why you want incremental algorithm, not because we need it for subsecond convergence today, but you want to be able to make your networks grow. Okay, to summarize, today's convergence times, actually I have to say in Qwest network, they are really good, and it's the best you can have with today's implementations or the timers. But here are the problem areas. Detection times, whether it was hardware or software, it was in multiple seconds, and that needs to improve. Without that, you cannot have subsecond convergence. If you don't know that the link is done faster than a second, we cannot actually have a convergence faster than a second also. The LSP propagation times were already sub-second. They were actually in multiples of hundreds of milliseconds, which is acceptable for sub-second. If you really want sub-second and 999 milliseconds is acceptable, then it is okay. But there is room to improve here. That could actually probably come down to less than 100 milliseconds. But anyway. And then, majority of the time goes to SPF rate limiting, to the SPF interval parameter, and that is actually hurting. First, it is the highest components of the convergence delay. Second, instead of grouping the SPF computations together, it actually spreads them out. So, knowing these problems, how can we reach subsecond ISAS convergence? The first thing is we need to have fast link failure detection. And for that, hardware detection is the answer. And in a network like Qwest, where majority of the links are point-to-point, hardware detection is achievable. And you need to ask your vendors that you are already selling me a product called MPLS fast reroute, and detection is the exact same component in that system. If you can detect it for MPLS, then you cannot have fast reroute there also. So that means you must have a solution there. I want a solution in my router for ISAS. You need to ask that. And if they did that, your convergence times will improve immediately. You don't have to have another component. That 3 seconds detection will become basically sub-second. The second thing, and I think this is the most important step here, is the adapting an adaptive and asymmetric uptime filter, because this is your safety. Without this step, you can go to unstable situations in the network. But if you have adaptive and asymmetric filters, whatever the rate of the change in the network is, you can always bring it down to a change once every 20 minutes. So this is very important. So given these two steps, now it's your turn. You can actually measure your router CPU utilization and such, and with this filter in place, you can get more and more comfortable. I'm not saying you should eliminate the timers all the way to 0 from the beginning, but you can get comfortable and you can gradually reduce it down to something that's acceptable to you. Maybe you don't need 0. Maybe 50 milliseconds is enough so that you have some safety or something. But as you get more comfortable, you can eliminate this limit, and step 2 is going to provide the comfort for this. And the final step is actually adopting an incremental SPF algorithm. And this is a must-have for scaling, having a larger network. I believe out of this 4-step recipe, the hardest is the step number 4. But for sub-second convergence with today's network size, it's not even required. However, it's good to have for scaling the network to large sizes. Well, I would like to thank quite a few people, but particularly I'd like to I'd like to thank Chris Cyber, Paul Murray, and Shankar Rao from Qwest for letting us do this analysis and measurement, and allowing us to share this with you. Questions?
Jeff Parker, Axial Wave, nice talk.
Thank you.
Is there any point in having the up for adjacency damp time max out to anything longer than the SPF refresh time, than the LSP refresh time? You're going to get that LSP anyway. Why not piggyback the adjacency up with that?
Actually, I didn't get the question. So
your adjacency up timer is effectively damping the rate of generation of LSPs.
Yes. So how much should be the maximum penalty for that?
So the maximum penalty for that could be 20 minutes or
yes, because
LSP refresh time, whichever is smaller.
the only difference is it depends on the implementation, because even though LSP is refreshed, that doesn't necessarily have to require an SPF computation, right? Because
Agreed.
if there is no change, you don't really have to do an SPF computation. But that's a good, I think this is probably a good bound on how much you want to be damping it.